Alright, welcome to Algebra and my kitchen. This is the first time I've ever done this, but we'll see how it goes. Wanted to talk to you a little bit about today. We're going to move into more of the algebra part of the course, and as you know, algebra is generalizing things. The algebra we do in high school, we generalize arithmetic. In this class, we're going to generalize some systems, both a set of numbers and operations on the numbers. And we're going to talk about groups and fields and rings. The first thing we're going to talk about is the number systems that we're going to work with, the natural numbers, the whole numbers, the rationals, the irrationals, the reals, and the complex. And we're going to show how they're interconnected and why one follows from the other. So we're going to start first with the counting numbers, which are 1, 2, 3, 4, 5, 6, 7, 8, 9. And those are a subset of the whole numbers, which is what we get just when we add 0 into the mix. And then the next step is we go to the integers, and the integers are just the whole numbers plus the negative numbers. Alright, this is how I like to picture this in my head. We start off with the counting numbers, and then we add the 0, so we get a slightly bigger circle, and then we add the positive integers and we get a slightly bigger circle. Alright, now one reason we can think of that the integers come into play is because when we try to subtract positive numbers, we don't always end up with a positive number, right? If we go 2 minus 4, we're no longer in our nice little set of whole numbers or natural numbers. So rational numbers can come up the same way if you think about, instead of subtracting, if you think about division. So for example, 2 divided by 3 is no longer an integer. It needs to be someplace else. So fractions and rational numbers, the same idea, right? Another way that we think about the rational numbers, of course, as you know, is with their decimal expansion. And rational numbers have decimals that either stop, like 0.5, or that repeat, like 0.3333 or 0.14141414, things like that. Okay, our next big circle when we go from the rational numbers to the next set is going to be the real numbers. And to get from the rationals to the reals, we add in the irrational numbers. That is, one way to think of the irrationals is they are the decimals that don't stop and don't repeat. And this has a great story regarding calculus behind it that's in your chapter 2 reading that we didn't do. But for example, if you look at the decimal 0.1 and then 0.14 and then 0.141 and then 0.1414 and so on and keep adding on the next decimal from the square root of 2, that will never stop and never repeat. But we can approximate the square root of 2 by rational numbers, the 0.1, the 0.14, and so on. So irrational numbers are actually quite interesting, and they are what we add to the rationals to get the set of real numbers. Now, a quick little ditty as well is the size of these circles aren't necessarily accurate at all. There are actually many, many more irrational numbers than rational numbers. We can actually count the rational numbers. We can't count the irrational numbers. A famous mathematician, E.T. Bell, once said that if you look out at the nighttime sky in Nebraska when you can see all the stars represent the rational numbers, and the black space represents all the irrational numbers. So there are that many more. Okay. When you put the rationals and the irrationals together, you get the reals. Okay. And now, as you know, once we get through the real numbers, that's not enough to solve every equation in the world. And so this imaginary number comes up, the I, the square root of -1, and we get the complex numbers a plus bi. Now, we aren't going to actually prove that that's all we need, but you guys might want to think about it. Just introducing that one square root, the square root of -1, allows us to solve any equation, any polynomial that we want. That gives us enough numbers, which is kind of odd. Right? Now, another thing that we can look at is, well, what if instead of doing a plus bi, we looked at a plus b times something else? And so, again, we're getting into this idea of generalization and the idea of groups and things like that, which we'll talk about a little more later.